Welcome. So the topic we'll be discussing in this lecture is floating point numbers and operations. So basically we'll be discussing how floating point numbers are represented in a computer. We'll be discussing a brief overview of that, and also we'll be discussing a brief introduction to floating point arithmetic. Okay, so that is the objective of this lecture. Fine. So to start with, let us start with normal numbers, how it is represented uh, in binary. Okay, let us not go for first floating point numbers. If you take a normal number, if it is a 32-bit number, say it will have 32 bits starting from bit 0, the the rightmost bit or the least significant bit is bit 0. Okay, then we have bit 1, right? Then we have bit 1, bit 2, bit 3, up to bit 31. Okay, if it's a 32-bit number, right? Then how will you find its value? Whatever bit 1, all these bits can be either 0 or 1, nothing other than that, because it's a binary number. Okay, so the leftmost bit will be multiplied with 2 to the power 0. I mean the rightmost bit, the least significant bit will be multiplied with 2 power 0, next with 2 power 1, 2 power 2, so on and so forth up to 2 to the power 31. Okay, so as a result, whatever we get, that is the actual value which is represented by the particular binary number. Okay, so whenever we talk about fractions, or floating point number, we talk about the binary point. We talk about that binary point. Okay, so in a decimal number we call this decimal point, but as this is a binary number we call this as binary point. So how this binary point suddenly comes with this, in the sense, in a normal number also, actually there is a implicit binary point to the right. Okay, to the right there is a implicit binary point, so which means after that there is nothing, or it is 0. Okay, so which is considered as a whole number, right? So in a normal binary value also, there is a implicit binary point to the right end. Actually there is a implicit binary point. Okay, suppose, assume that instead of keeping this binary point in the right end, let us represent in the left end. Okay, instead of keeping this binary point at the right end, if we keep this binary point in the left end, then how this number should be represented? So by default the binary point is in the right end. In that case the binary number will be represented like this. Okay, but if the binary point is in the left end, then how the number should be represented? Then the number should be represented like this. Okay, whatever the first binary value which comes after the first binary value which comes after the binary point should be multiplied with 2 to the power minus 1. The next number will be multiplied with 2 to the power minus 2, next will be multiplied with 2 to the power minus 3, and so on and so forth it goes on. Okay, so that depends on the size of the number. If it is a 32-bit number, then it will go up to 2 to the power minus 32. Okay, so here one thing you should do, you should see, for whole numbers we start with 2 to the power 0 and it goes to 2 to the power 31. But in case of with numbers with a binary point, it starts with 2 to the power minus 1 and it goes up to 2 to the power minus 32 for a 32-bit number. Okay, if it is a 64-bit number, it will start with 2 to the power minus 1 and it will go up to 2 to the power minus 64. Okay, for a 8-bit number it will start with 2 to the power minus 1 and it will go up to 2 to the power minus 8. Okay, so whatever the value you get, you have to sum up, right? So again, this is actually interesting. If you see 2 to the power minus 1, it is 0.5. Okay, 2 to the power, so assuming this is 1, assuming this bit 31 is 1, if you multiply it with 2 to the power minus 1, it is 0.5. Assuming this bit as 1, if you multiply it with 2 to the power minus 2, it is 0.25. Okay, so if you see 0.5 is exact, 0.25 is exact half of 0.5. Similarly, if you see this is point, okay, this is 0.12, this is 0.125. So which is nothing but it's half of this, so on and so forth, it continues. Okay, so say how it happens in the normal binary. This is 1, this is 2, this is 4. Okay, it's a multiple of 2, right? 8, 16, 32. Similarly here it goes in this way, 0.5, 0.25, 0.125, so on. So every other number is nothing but the half of the previous number. Okay, right? So this is the very basic understanding of uh, numbers with implicit binary point at the beginning. Okay, at the left end, right? Fine. So with this representation with 32 bit with 32 bit, if the number of bits can occupy is 32 bits, then with this what is the range of numbers we can represent? So the range of numbers that we can represent is from 0, starting with 0 to approximately this much, 0.9998. Okay, what is 0? If all these bits are 0, if all these 32 bits are 0, okay, with a implicit binary point at the left end, then that value is 0, or you can say 0.0, right? Whatever it may be. If all these are 1, if all these 32 bits are 1, then whatever we have discussed previously, it is nothing but 0.5 plus 0.25 plus 0.125, so on and so forth. Okay, 0.25 plus 0.125, so on and so forth. If you add all these things, what you will get is this number, approximately equal to 0.999998. Okay, right? So otherwise this can be represented, this number 0.9998 is equivalent to 1 minus 2 to the power minus 32. Okay, so instead of saying this, we can also represent this as 1 minus 2 to the power minus 32. Okay, so with 32 bit numbers, with 32 bit with 32 bit and with implicit binary point at the left end, the range is from 0 to 1 minus 2 to the power minus 32. Okay, so this much. So this is the range of numbers that can be represented with 32 bits. So how many numbers we can represent with 64? What is the range that can be represented with 64 bits? So that is between 0 to 1 minus 2 to the power minus 64. Okay, right? For n bits, it will be 0 to 1 minus 2 to the power minus n. Okay, so this is the generalized one. Okay, so this is a specific example for 32 bit, and this is the generalized one. So if there are n bits with an implicit binary point at the left end, then this is the range of numbers that can be represented, something between 0 to 1 minus 2 to the power minus n. Okay, right? Fine. Okay, so this is the basic concept we have discussed, where the binary point is represented at the left end. Okay, but actually there are a few disadvantages in this. So actually with this, what happens in the sense, so it means that this is the minimum number you can represent, and this is the maximum number you can represent, or this is the maximum binary number you can represent, and this is the minimum one you can represent, right? No, not that. In binary, as a floating point, as a floating point number, not exactly floating point, we are not calling this as floating point, because we are going to define floating point somewhere else as a fractional number. Let me call it as a fractional number. As a fractional number, with this representation, this is the maximum value you can represent. Okay, because all are 1 means this is what you will get. Okay, right? Okay, if it is non-fractional in a normal case, then this is the maximum you can represent, which is nothing but 2 to the power 32, right? But actually this number is also, this is the highest fractional value can be represented in this format. that is by considering a implicit binary point at the left end. But actually this number is very small, because in most of the scientific calculations you will be using still what you call I mean you will be using a fractional number uh, with more precision. Okay, so this may not be sufficient. Okay, so here the precision is limited, right? So this may not be sufficient. So in that case, what you should do, in the sense, we should go for a floating point number. This is called as fixed point number. Actually this is also a fixed point, this is also a fixed point, right? Why we call this as fixed point? Because the point is fixed, the binary point is fixed. Here the binary point is fixed in the right end in case of whole numbers. Here this is a fractional number, but here also the binary point is fixed in the left end. The binary point never moves in this format. The binary point never moves. Here it is always in the left end, here it is always in the right end. Okay, so we are going for the next style of representing by which this binary point can move from one position to another position, so that what we can do, in the sense, the range of values that can be represented can be increased, right? So such numbers are called as floating point numbers. So what is a floating point number? In the sense, this binary point can move at different locations depending on the number what is to be represented. Accordingly the binary point can be placed. As the binary point is moving, it is called as floating point numbers. The binary point is floating from one location to another location, so it is called as floating point numbers. Okay, right. So generally how we represent floating point numbers? In decimal. In decimal, this is typically we represent the floating point number. Some number m1 dot m2 m3 m4, it may go on. Okay, into some base to the power exponential. Okay, so this base can be, generally it will be 10. In decimal it will be 10. Okay, in binary it will be 2, right? In binary it will be 2. So okay, in binary it will be 2, right? So this part is called as Manti-saw. Okay, I'm sorry, some technical thing. Okay, so this part is nothing but Manti-saw and the base and the exponent. Okay, so what we are going to do is we are going to represent the binary numbers also in this format. Okay, the binary numbers also we are going to represent in this format with Manti-saw and exponent. Okay, here the base will be assumed as 2. Okay, so right, so the implied base will be 2. Okay, so 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 this number, if you see, it is said to have 7 significant digits. Okay, that is, after decimal point, how many digits it has? 1 2 3 4 5 6 7. So such a number is said to have 7 significant digits into base to the power something. Okay, right. Okay, so if you have 24 bits, to represent Manti-saw. Okay, if you have 24 bits to represent Manti-saw, then all 24 ones. Okay, all 24 ones, which will be approximately equal to this much value, right? all 24 ones, it will be approximately equal to this much value. Okay, so this is nothing but whatever we have discussed previously. That way you have to calculate 2 to the power minus 1 plus 2 to the power minus 2. Okay, all these things up to 2 to the power minus 20 minus 24. Okay, 2 to the power minus 24. So if you do all these things, what you will get is this. This is what you will get, right? Okay, so if you do that, so this is the number that will be uh, equivalent to that. Okay, so yeah, so fine. But actually here what you have to do is, yeah, you have to perform all these additions. When you perform all these additions, this is what you will get. Okay, so this is the maximum number that can be represented in this. Is we are discussing only Mantissa part. We are not going to we are not yet started the exponential part. In Mantissa part alone, this is this much number you can, this is the maximum you can represent, and this is the minimum value you can represent. Okay, this is the minimum value you can represent, where all 23 bits are 0 and only one bit is 1, which is equivalent to this, right? Okay, so actually IEEE has suggested one way of representation for for floating point numbers of in binary. Okay, so say for example, if you have 32 bits, then what IEEE suggests in the sense, use the least significant 24 bits to represent Mantissa. This 24 bits will be used to represent the fractional Mantissa. Okay, and the binary point is assumed to be here. Okay, there is no explicit binary point, it is implicit. The binary point is assumed to be here. Okay, the binary point is assumed to be here, right? And this is the exponential part. Okay, to represent the exponential part, 7 bits were reserved, and the most significant bit is used to represent the sign bit. Okay, so if you add all these things, 1 plus 7 8, 8 plus 24 is 32. So this is how IEEE suggests to use. Okay, and also IEEE assumes that the number before the, what you call, the number before the floating point as 1. Okay, because that is what you can have maximum, either 0 or 1, right? So this is how IEEE suggests to represent a floating point number. Okay, say for example, if you consider this floating point number, point 0.000405671 into 10 to the power 12. Okay, but instead of representing this number like this, it can be represented like this also. That is you can left shift these zeros. You can left shift this 3 times. If you left shift this by 3 times, for every left shift you have to decrement the exponential part by 1. Okay, when you left shift by 1 time, the decimal point will come here. Okay, here is a decimal, right? Decimal point will come here and this will become 11. When you shift 2 times, the decimal point will come here and this will become 10. When you shift 3 times, the decimal point will come here and this will become 9. Okay, so like that is also applicable in binary. Say for example, in the Mantissa you have something like this, and the exponent part is something like this, which represents 2 to the power 8. Okay, the exponentials, there are 7 bits, no? So say that represents 8, so which means 2 to the power 8. Okay, but here you can see in the Mantissa the first 3 bits are 0. So it means that the trailing zeros does not make any sense in fractional numbers. Okay, I mean, it makes sense, but it can be adjusted. Okay, so what you are doing, you are shifting it 3 times. So when you shift it 3 times, whenever you shift, you decrease 1. So when you shift 3 times, it becomes 8 minus 3. So only we have this part. Okay, we'll take only this part, that is this, and that can be multiplied with the exponential 2 to the power 5. Okay, so So this is called as normalizing a number. This is called as normalizing a number. A number which is brought into a form so that all the available Mantis digits are optimally utilized. Okay, optimally utilized. Okay, so so otherwise here these zeros are unnecessarily occupying the space. Okay, so that we are moving this to the left and we are adjusting the exponential part. Okay, so this is normally we do in floating point arithmetic. Okay, right. So what is the procedure for normalizing a floating point number? This is the procedure. Okay, until the MSB of Mantis is equal to 1. So here if you see, this is the MSB. So the MSB is not 1. So until the MSB is not 1, shift the Mantis to the left or right depending on the requirement. Okay, shift the Mantis to the left or right. Okay, either decrement or increment 1. If you are shifting left, you have to decrement 1. If you are shifting right, you have to increment 1. Okay, if you are shifting left, you have to decrement 1. If you are shifting right, you have to increment 1. Okay, sometimes you can also shift right. It is not that we won't shift right, you can also shift right. Okay, so when you are shifting left, decrement for every shift, decrement the exponent, and for every left shift, decrement the exponent. If you are shifting right, for every right shift you have to increase the exponent. Okay, so here is another example. So if you, here the exponent is 2 to the power minus 62, you can see here at the MSB there are 3 zeros, so you can shift it left by 3 times. So it will, so you have to subtract minus 3. So minus 62 minus 3 is minus 65. Okay, similarly you can see here this is 1.000. so this actually you have to right shift so that this 1 will come here. Okay, but when you right shift you have to increase the exponent. Okay, so this exponent will become 64. This exponent will become 64. Okay, right, but actually these two cases will create overflow. This two, I mean this will create underflow. The first one will create underflow because it is going up to minus 65. Okay, even if it is a 64-bit number, you can have maximum from what do you call, you can have maximum from 2 to the power minus 64 to 2 to the power plus 63. Okay, you can have 2 to the power minus 64 to 2 to the power plus 63, not beyond that. So it is going to minus 65, so that condition is called as underflow. Similarly, if you see this is creating an overflow. It is going to 2 to the power 64, which is also not in the range. Okay, so these conditions are called as underflow and overflow, which will create an exception. So if the result is underflow, means the value is so less that it cannot be represented with the given number of bits. That condition is called as underflow. I mean you are going lesser than the minimum number that can be represented. Okay, so this is the minimum number you can represent, but you are going beyond that, which is 2 to the power minus 65. Okay, overflow means you are trying to represent beyond the maximum number. The maximum number you can represent with 64 bit is 2 to the power 63, but you are going beyond that. So that condition is called as overflow. Okay, so there is something called as excess notation. We will come back to this later. We will discuss that in one context. Okay, so as I already discussed, so this is how IEEE suggests. So yeah, so okay, yeah, so this is not an IEEE representation. The original one which we have discussed, this is a sample representation. I have told this as IEEE, but this is not an IEEE. This is a sample representation. But actually IEEE suggests this type of representation. If you see in IEEE representation, what happens is 23 bits for Mantis. Okay, if it's a 32-bit number, then IEEE suggests to use 23 bit for Mantis, 8 for exponent, and one sign bit. Okay, so if you add all this together, it is 23 plus 9, which is 32. Okay, so which is for an 32-bit number. In case of 52-bit number, IEEE suggests to, in case of 64-bit number, In case of 64 bit, if there are 64 bits available, then IEEE suggests to use 52 bits for mantissa, 11 bits for exponent, and 1 for sign bit. Okay. So you may ask, what is the difference between 32 bit and 64 bit? 32 bit is called as single precision and 64 bit is called as double precision. Okay. So in normal programming languages, this single precision is called as floating point numbers. In normal programming language in C or Java, this single precision is called as floating point numbers, whereas double precision is called as double numbers. Okay, we say single, we say float and double. No, this is the difference. In float, for mantissa you have only 23 bits, and for exponent you have only 8 bits, whereas for double mantissa you have 52 bits, and for exponent you have 11 bits. So the range will increase. Okay, so this is the single precision and this is the double precision. So this is what IEEE recommends. Fine. Okay. And another important thing of IEEE is, so IEEE provides 8 bits for exponent, but here there is some a little trick is involved. So normally with 8 bits, this is the range of numbers that can be represented with with signed numbers. This is the range can be represented -127 to +128. Okay, -127 to +128. Okay, see this, first of all I want you to give clarity on this itself. See, minus, this is, you have 8 bits, right? 1 2 3 1 2 3 4 5 6 7 8. Okay, 1 2 3 4 5 6 7 8. Okay, this is for sign bit, this is for sign. This will be either 0 or 1 for